Geometry, Lesson 7.5, Areas of Regular Polygons. I'm going to do a short introduction here. There's a lot to learn about finding the area of polygons, and I want you to stop the video right now and get note paper out, because there will be lots of notes. So let's talk about circles for a second. Circles can be inscribed in and circumscribed about any regular polygon. So from previous lessons we've learned that an inscribed circle will have the same center as your polygon, and with our compass we would set our compass at the center C, and we would set it up so that we have a circle that fits inside of this polygon, which is a triangle, by using the midpoint of the side as a radius. We can also circumscribe about the polygon, and we did that by measuring from the center to the vertex. And if we've done this correctly, the circle will touch all the vertices on the polygon. So to the left we have a triangle, to the right we have a square, and there are sets of relationships that are set up when we inscribe and circumscribe circles in our polygons. So the centers of the inscribed and circumscribed circles are the same point. So this outer circle and inner circle both have the same point. You can see the same thing happening on the square. The inner circle, its center is center C, and this outer circle, its center is center C. The common center of these concentric circles is called the center of the regular polygon. So not only is this the center of the circles, it's the center of the polygon also. And the expression concentric circles is when you have a smaller circle and then a larger circle, and you could continue on with another larger circle, and they're all equidistant from each other. The area addition postulate states that the area of any polygon can be found by dividing the polygon into triangles and then adding the areas of the triangles. And we've been doing this in the last few lessons. Let's take a look at the square. If we draw diagonals on this square, we have two large congruent triangles. We also have four small congruent triangles. And with this, we can actually use 90 degree triangle or right triangle properties to solve. By drawing segments from a regular polygon center to each vertex, the polygon is divided into an unknown number of isosceles triangles. So depending on which polygon that you have, and in the square we have 1, 2, 3, 4 isosceles triangles. N will be, for a square, 4 isosceles triangles. For a hexagon or an octagon, it'll be a different amount, and we will discover these things. The base of each isosceles triangle is a side of the polygon. So the base of each isosceles triangle, let's pick the triangle at the bottom of the square. It has two lengths, and it's isosceles, so let me get my pen out here. So we know that these will be congruent, and it says that this base is a side of the polygon. So side is labeled S. So this would be another side, and I won't be able to draw it. But this is a square anyway, so you know that all of these sides are congruent. The legs are the radii of the circumscribed circle. So a leg of one of these isosceles triangles is also a radius, and you can see that right here. We've got radius, and we have a leg, and this leg is actually also the radii of the outer circle, the circumscribed circle. So if the leg of this isosceles triangle is a length of 4, the radii of the circle is 4. The altitudes to the bases are radii of the inscribed circle. So here's an altitude. Let me highlight that so you can see it a little better. So here's an altitude. And the altitude to the base is a radius of the smaller circle, the inside circle. So if the altitude to the base is 3, then the radius of the inscribed circle is 3 also. A radius of a regular polygon is the segment that joins the center and the vertex of the polygon. So let me say that again. A radius of a regular polygon is the segment that joins the center and the vertex of the polygon. So polygons have a radius also. We know they have a center, just like a circle, but they also have a radius. And the radius has the same properties that we've learned about circles. So all the radii in a regular polygon will all be congruent lengths. And it's the segment that joins the center of the polygon to one of the vertices. A central angle of a regular polygon is the angle formed by 2 radii drawn. So when we draw 2 radii in our polygon, we create a central angle, and that will be the angle that is in between the 2 radii. We have a new expression here, apothem. The apothem of a regular polygon is the perpendicular segment that joins the center with the side of the polygon. So here's an apothem right here. And many of you are going to say, wait, this looks like an altitude. Well, you're correct for some polygons. In some polygons, the altitude will be the apothem. In some, it won't. So for a triangle, the altitude will run all the way from the top of a triangle to its base. In a polygon, you're going to go from the center of the polygon to the base at a 90-degree angle. This will get confusing as we start working with our area formulas, because in the past we've used small a to be alternately altitude, and the a from a squared plus b squared equals c squared. So it's important that you understand the concept of the polygon and actually use the word apothem when you're working with these. Let's do an example. Let's take a look at our polygon. This polygon has 1, 2, 3, 4, 8 triangles, so it's an octagon. Find the following angle measures in a regular octagon. So we're going to find the measure first of a central angle. So the central angle is this angle Let me highlight it for you. Right here that we're going to be solving for. If you can see what they've done, they have radii drawn in the polygon. And we have a triangle here that's formed. The measure of angle P, and it's difficult to see the P on the drawing, but this is a P, it's PQR, equals 360 divided by 8, which is 45. Well, where did that 360 come from? The 360 is actually from a theorem that we're going to learn in a couple of slides. So, for some reason they've introduced this before we've done the theorem, but that's okay, which will be 45 degrees. If you were to take all 8 of these central angles and add them together, they would equal 360 degrees. The radii divide a regular octagon into 8 congruent isosceles triangles. So each one of these is isosceles with 8 congruent central angles. So if I knew that just one of these sides was, say, 4, one of these sides of the triangle was 4, then I would know that each one of these radii are 4. So our central angle here is 45. The second part of that example, it says the measure of each base angle, and we are talking about these two angles because remember, this is an isosceles triangle. In the triangles is formed by consecutive radii. So the measure of each base angle in the triangles is formed by these radii that we've drawn. So let's take a look. The measure of angle P plus the measure of angle PRQ, which is this one right here, and the measure of angle PQR, which is this base angle, equal 180. We know that because the angles of a triangle equal 180 degrees. And we also know that angle PRQ and angle PQR are equal to each other. And that's because of isosceles triangle theorem that tells us that the base angles are congruent. So let's solve for their measure. And we already know that angle P was 45 degrees from solving problem A. And we can add these two measures, and they skipped a step here. Rather than rewriting these like they did up at the top of the problem, they've shortened, they've done mathematical substitution, and they've shortened. We now have 2 times the measure of PRQ. Just like we do when we do our theorems, we're substituting, and because these are 2 equal base angles, we can call them the same angle. So adding all 3 of these angles together, we have 180 degrees. If we subtract 45 from both sides, we have 135. And now if we divide by 2, we have 67.5 degrees. So each one of these base angles is 67.5. We know the other angle was 45, and that will add to 180. So we're applying the triangle angle sum theorem to find the measure of each base angle. And we, in the last slide, learned how to find the measure of the central angles. So that brings us to our theorem. The radii, I'm sorry, let me switch here. The radii of a regular n-gon, so that's any polygon, that's regular, divide the polygon into n number of congruent isosceles triangles. And remember, there will be a different number, and you will notice a pattern soon. In the octagon we had 8. In this pentagon we have 5 isosceles triangles, and form congruent central angles with measures of 360 degrees divided by the number of triangles. Okay? So in the octagon we had 360 divided by 8. In this instance we would have 360 divided by 5, using the same drawing. The area of each isosceles triangle formed by the consecutive radii can be found by using the triangle theorem. Area equals 1/2 base times height. So what we're going to do is to solve area of some of these. Now there are other formulas and you'll learn them, but just going to basics, you can always solve for the area of each triangle and add them together. So you can solve for the area of one triangle using 1/2 base times height, and then you can multiply by 5. So we're going to substitute now, and we're doing this because eventually this will lead us to our formal area formula. So we're now going to call these sides rather than legs. And we're going to substitute S for the expression base in this formula. So the base was always a side. It was always the bottom of the triangle, and we can think of it this way. And instead of saying B, it'll be 1/2 S. And we're going to use the A for apothem for the height. Now you can see how the apothem fits in. The apothem is actually the height of the triangle formed by the radii. So this would give us a formula of A equals 1/2 SA. Some books that you'll deal with, or if you're looking on the internet for help, they'll have it as 1/2 AS. That's fine. It's the same formula. So in this instance, what I did is I took our original formula, and if you have trouble remembering the SA, as long as you can remember which parts go where, you'll be fine. We've converted that now to 1/2 SA, which is the same formula. So if I want to solve this isosceles triangle, I can solve it using 1/2 SA. But wait, we have more triangles in this polygon, and we want to solve for the whole polygon. So we're going to take this formula and add number of sides to it. So in this instance, we would have 5 sides. So the number of sides times the 1/2 SA. We're going to skew that formula around to get to where we need to go to. And we're going to we're going to use associative and commutative property to combine the N and the S together and have the A on the outside of the parentheses. And why are we doing this? Because way back when you learned a perimeter formula, and that was perimeter equals number of sides, the number of sides times the side length. What you're doing is basically saying 1/2 the perimeter of each triangle times its apothem. And, or 1/2 the perimeter of the polygon now times the apothem. And this leads us to the formal formula of 1/2 PA. So you're really now doing 1/2 the perimeter of one of the triangles times the apothem. This leads us to the actual formal theorem. The area of a regular polygon is 1/2 the product of its apothem and its perimeter. So, A equals 1/2. On the last slide we said PA. They turn it around because they love alphabetical order, and it's now called AP. This is the final theorem you should have in your notes. However, going back, let me tell you something. If you have these bits of your formula also in there in your notes with a drawing, what you can do with these is sometimes you won't have all the information you need to get directly to 1/2 AP, and you can use some of these pieces to get halfway there. That will happen more when we get down to doing some more complicated shapes. But for right now, in your notes, put 1/2 AP is the area of a regular polygon. So this can be used not only on a pentagon, but it can be used on an octagon, a hexagon, a nonagon, and so forth. Sorry, I keep going backwards. All right, example 2. Let's use this. Find the area of the regular octagon. Let's look at what we have. We have one side length of 10 centimeters, and we have an apothem length of 12.1. So, to do this problem now, to find the area, you're going to do 2 basic steps. Find the perimeter, which is P equals NS, and P equals 8 times 10. Wait, where did I get that? Going back, what does N mean? It means the number of sides of the octagon. So 8 times the length of 10. So the perimeter is 80 centimeters. Now we can take that P for perimeter and substitute it into our formula. And our formula is 1/2 AP. So 1/2 apothem, 12.1, times the perimeter, 80 centimeters. And multiply, and you have 484 centimeters squared. One thing I want to note is because the apothem is an altitude of an isosceles triangle drawn from the vertex of a central angle, it's also a perpendicular bisector of the side of the polygon. So that means if this side length here is 10, when we drop this apothem, or which is also an altitude, we now have 2 segments of 5. This will help you solve some of these polygons. Example 3. Find the area of a regular hexagon. Remember that a hexagon has 6 sides. We can see the side length is 4 inches. We're going to find the perimeter. So P equals NS. P equals 6 sides times 4 inches for 24 inches. Now that we have our perimeter, let's move on to the second step. Find the measure of the central angle and the base angles in the isosceles triangle PCQ. So the measure of angle CPD and CQD, which are the base angles, are equal. And in a hexagon, these are equilateral triangles. This doesn't happen in all polygons, but make a note of that. For hexagons, the triangles formed by the vertices are equilateral triangles. So that means that each one of these angles will be 60 degrees. So, one half, 80 minus 60, will equal 60. Now, for the third step, we're going to take that triangle, PCQ, and because it's equiangular and equilateral, we can now say that PQ is 4 inches, so guess what? CP is also 4 inches, and CQ is 4 inches. And remember that the apothem divides this side in half, so DQ let me try again here, is 2 and DP is 2. For the fourth step, we take triangle CDQ. We know it's a 30, 60, 90 triangle because we know that these sides were all part of an equilateral triangle, and we have some side measures here, and we can actually use the 30, 60, 90 triangle theorem to solve for our apothem. So if DQ equals 2, we know that the hypotenuse here is 2x, which will be 4, and that the apothem will be 2 square root of 3. By using our ratio x square root of 3, and 2x, the apothem is the long leg, DQ is the short leg. And step 5, substitute into our formula for solving for the area of the polygon. So we have 1/2 AP. We have 1/2. We now know that this length was 2 square root of 3. I'm going to try to write it over here. So this was the apothem. 2 square root of 3, and the perimeter we solved back on the first slide for example 3. So that was 24. And we can multiply them all together. 2 times 24 is 48, divided by 1/2 is 24, square root of 3 inches squared, which is approximately 41.6 inches squared. Now this was 5 steps to do one problem. Right now, take example 3 from all of these slides and write them down on your paper all together, and actually write in the steps 1, 2, 3, 4, 5, because you will use this over and over and over again. So we have some other formulas that you might use as you're coming across information, just because you won't have the information you need to solve other things. So you can solve an apothem if you know the height, and this works particularly well in triangles. The apothem is actually from, remember, the central angle to the base, and or side now we call it. You could see the apothem there, but this is an apothem also, and this is an apothem also. So the apothem is actually 1/3 the total height. So sometimes you'll need to solve for an apothem. You won't have anything but the height of the triangle. Then you can use this formula, A equals 1/3 of the height. Sometimes you'll only have a side length, and so then you can use square root of 3 over 6 times the side length. And sometimes you need to solve for a radius, and all that you will have is a side length. Well, that is square root of 3 over 3 times the side length. So write these formulas and how to use them in your notes. You'll be using them on your homework. So let's look at the homework, numbers 1 through 12, 15, 17, 19 through 21, 23, 25 through 39. I'm actually going to do some of the problems from your homework. That's okay. When you do your homework, because you know what the answer is, please don't just give me the answer. You need to show your work so that we can assess how well you're doing. So number 14, it says use theorem 7.5.2 to find the area of each regular polygon. So here's our area formula, 1/2 AP. But we're going to use, in this case, just because we're solving a little differently, 1/2 A and S. Remember, that was one of the formulas we used to convert to this one. So that's why it's important to write this down. We're using this to help develop your understanding. So this is 1/2 the apothem times the number of sides times the side length. So we have 1/2 the apothem, there's the apothem, 4, times the number of sides, which is triangle is 3 sides, and the side length is 13.9, and that multiplies to 83.4 inches squared. Number 16, we're going to do the same thing. So you have a side length and you have your apothem given. When you have the apothem, it makes these problems much shorter. It's when you have to solve for it that you have to add the extra steps. So 1/2 AP will be 1/2 A times N times S, which is the same as saying perimeter. And we have 1/2, the apothem is 29. There are 8 sides with side lengths of 24. It's 2784 meters squared. So I actually prefer this formula to AP, and the reason I do is because you don't have to do the first step of solving for the perimeter. You can actually put it in your formula. Okay. We're going to find the measure of the apothem of a regular triangle. And this is a good example of what happens when we have triangles and we're trying to solve for pieces of these triangles. It says here the altitude equals 21 centimeters. The altitude is the same as saying the height. And so this whole piece from the vertex at the top of this triangle to the base is 21. We're solving for the altitude, which is this piece A here, which goes from the central angle down to the base. Okay? So the altitude is not, or the altitude is the same as the height of the triangle. Sorry. But the altitude is not the same as the apothem. That's what I'm trying to say. So apothem equals 1/3 of the height. Number 20, find the measure of the apothem of a regular triangle. A side length equals 2 the square root of 3 feet. Okay. So use the formula for apothem when you have a side length. So that formula is area equals square root of 3 over 6 times S. And it's square root of 3 over 6 times side length is 2 square root of 3. So I'll let you go on and continue to solve for that. 21, find the measure of the apothem of a regular triangle. Its radius equals 12. So radius is 12 yards. This is my hint for you, use the 30, 60, 90 triangle theorem to solve for the short leg, which is A, your apothem of the triangle. Redrawn, this triangle right here looks like this. And you already know that your radius equals 12. So go ahead and solve using the ratios for a right triangle, 30, 60, 90 right triangle. Number 24 says find the measure of the apothem of a regular hexagon and then use theorem 7.5.2 to find its exact area. So I wrote out some steps for you here. Basically, you should draw radii to form equilateral triangles. If the side, remember this is side, is equal to the radii. Now these are radii, but they're also the same length. That means that this is 15. Okay? So you have a side length of 15. That means your radii are all 15 on these triangles. Redraw the triangle, just like I did in the last slide, with the altitude and insert the values using the ratios. The apothem length, this A length here, apothem, is the same as the long leg of your ratio, the x square root of 3. Once you've found that long leg, you can solve for the area using this formula. Homework number 25 is the beginning of a table. And I wanted you to see how one of these is worked out. I've gone ahead and I've drawn a triangle. It's an equilateral triangle. It says that there are 3 sides in the regular n-gon. So that's how I know it's a triangle. If it says it's 4 sides, it's a square. If it's 6 sides, it's a hexagon, and so forth. The side length is 6, which means this apothem that I drew divides this side into 2 pieces of 3. Now I have lengths for a triangle here that's a 30, 60, 90 triangle. And we have the long length is, the long leg length is 3. And we're going to be solving for the apothem. And we're going to solve for this radius. So the short leg is the apothem, and the short leg equals the long leg divided by the square root of 3. I know this from working with the ratios. So go back to your notes about the ratios and how the long leg relates to the short length. Okay, so the long leg was 3 divided by square root of 3. If we go ahead and rationalize this and multiply by 3 over 3, we end up with square root of 3, which equals a. So this a is the square root of 3. Okay? And knowing that that's the square root of 3, the other part of the ratio tells us that the radius is 2 times the short leg. So that would be 2 times the square root of 3. So the radius will be 2. Square root of 3. Now you have your pieces. You have 3 square root of 3 and 2 square root of 3. And you can solve using the formula. So 1/2 square root of 3 times 3 times 6 equals 9 square root of 3 units squared. So the A was the apothem, the N was the number of sides, and the side length was 6. Now there's another way to solve this also, and that's by going ahead and using the formula for an equilateral triangle. So if you have that in your notes and you've solved enough to know, you can find this out. So the area of an equilateral triangle is square root of 3 over 4 side squared. So you know that your side length is 6. And you can substitute into the formula. You end up with the same answer. So this was 9 square root of 3 units squared. Using the 1/2 AP, it's 9 square root of 3 units squared. The reason we used this was because we had to have the length of the apothem solved and the radius solved. But we already knew what the area was, and now this confirmed it. So that's it for this. I know this is going to be difficult. I'm available for help, and we'll get through this. Even if we have to extend for a week, that's okay. Just please ask questions when you have them. Sorry about the lawnmower guy, and we'll see you soon.